Good morning. It's a great pleasure to introduce Professor Michel Grabisch. He's a full professor at the University of Paris, Sorbonne, and is a leader in his field, and is the head also of the microeconomics theory department. And he has a long experience in decision theory, order, permutation, cooperative game, and also on discrete mathematics and operational research. He is co-editor of different journals that are leading in the fields. Quarterly Journal of Operational Research, Order, Mathematical Social Science, Annals of Operational Research. A lot of journals that have a great impact on our community. Imprecise Probabilities is well known in Imprecise Probabilities since he published more than 130 papers on journals. And he is writing also 5 books. So I don't want to spend more time, but it's a great pleasure that you accept our invitation to have a plenary talk at ESIPTA. Thank you.
So, thank you very much, Barbara, for your kind introduction. Thanks to the organizer for inviting me. So, it's a long time ago I participated to the first ESIPTA conference. So I'm very glad to come back. And I am also very glad to come back to Oviedo, where I have been several times visiting people in the university, especially Pedro Miranda and other people. So this talk is about essentially cooperative games, but you will see that there will be many connections, especially with decision making and therefore with imprecise probabilities. And more generally with discrete mathematics and operation research. So cooperative games is a very simple mathematical object. It is just a set function vanishing on the empty set. This is why they are encountered in many domains of discrete mathematics and their applications like, of course, game theory, but also essentially decision theory, and also related to imprecise probabilities and combinatorial optimization, and so on. So, an important notion here is the notion of core. If you have a game, the core of a game is something, a very central notion, which has also interpretations in the fields I just mentioned. Okay, and the core is. In fact, for many games, the core is empty. And the big question is under which condition, for which games, the core is a non-empty set. Okay? And this was discovered a long time ago by Shapley and Bondareva. And they called the set of games with a non-empty core balanced games, because the central notion behind balanced game is the notion of balanced collection. So in this talk, I will essentially speak about balanced collection, which is a combinatorial notion. It's generalizing the notion of partition of a set. And I will also explain what we can do with this balanced collection. You will see there are many applications in game theory, but not only. And also I will finish with the structure of the set of balanced games. Okay, so this is the outline of my talk, exactly what I just said. I will start with basic notions of TU games, then balance collection, then how to apply them, and finally the geometry of the set of balanced games. Okay, so let's start immediately with the notation. So throughout my talk, I will consider capital N as a fixed finite set of n elements. You can think this is a set of players, but you can also think it's a set of states of nature and so on. It is not important, in fact, yeah? And subsets of n will be called coalitions, because this is the usage in game theory, but you can think this is just events in decision theory. Okay? So now a game with transferable utility in characteristic form. So this is a very long name, so I will simply say later this is a game, okay? It is a set function, with the only restriction is that the value at the empty set is 0. This is the only restriction. So it is very, very general family. Okay. The second notation I will use very often is the notation of for payoff vector. So you can imagine n is a set of players. V of a coalition S is, let us say, it's a benefit this coalition can earn by cooperating together, okay? And so if they cooperate all together, the value V of n is the benefit of the game, okay? And so this benefit has to be shared among the players. And X is a payoff vector, that is to say, it's a way to share the total benefit among the players, okay? So, so it's a vector in R to N, and for every coalition S, I will denote by X of S simply the sum, the total amount given to this coalition. Okay, so this I will very often use. And the aim of cooperative game theory is to find what is called the solution of a game, that is to say, how to find, to define a payoff vector which is satisfactory for every player under some rationality condition, okay? So, usually, of course, you impose that the total amount you distribute is the total benefit, okay? This is called an efficient payoff vector. Okay, there is no waste. So now we are ready to see what is the main notion of this talk. It is the core of a game. So it is a set of payoff vectors which are efficient. So you share the whole cake. And this is the central condition. To every coalition of players, you ensure that what you give to this coalition is at least equal to the benefit V of S this coalition can achieve. Imagine you give less, then the members of the coalition S will say, oh, so there's no way to play this game. Let us play separately, and we leave the coalition, the grand coalition N, and we cooperate together without the rest, okay? So that's why when the core is non-empty, it's a guarantee of stability of the game. If the core is empty, it means that there is some coalition for which this inequality is not satisfied. And so this coalition will leave, okay? So this, just to explain the story behind game theory. So now let's see the same thing but in other domains. So the first domain you are interested in, especially in this conference, is decision theory. Then you consider capacities. Now, capacities is a special kind of TU game with the property of monotonicity. You impose, in addition, that the function V satisfies monotonicity with respect to inclusion. Okay? And for example, if you take a set of probability measures, you take its lower envelope, then you get a capacity. This is the connection with imprecise probability. Of course, probability measures are themselves capacities, which are additive. And now, what about the core? So if we translate the definition of the core under this new restriction, you will see that it is a set of vector x, so it's no more a pair of vector, no, it's something else. Still you have this condition, but now the total x of n, the sum of all the coefficients should be equal to 1. So this is merely a probability measure. So the core can be interpreted as a set of probability measures dominating the capacity V or compatible with the capacity V, okay? So this is an important notion. But if you go to combinatorial optimization, you will find the same things under different names. Especially in this field, they consider that the game is submodular, and because V is appearing as the rank function of a matroid. And also the people there in this community are interested into the core, but with the reverse inequality, so it's called the anti-core. We call this the anti-core, and they call it the base polyhedron of V. Okay, so you recover the same things in many different fields. Okay. Well, for the rest of the talk, I will stick to the vocabulary of game theory to simplify the things. So now, what about the balance collections? So, 50 years ago, Shapley introduced the notion of balance collection, which is the following. So you consider a collection of subset of a collection of coalitions, okay? And to each of them, you assign a weight, which is called the balancing weight, okay? And in such a way that these weights, which are positive, must satisfy this equation. What does it mean? You can interpret it in two ways. First, a mathematical way. You say, this is just to say that the vector 1n, which is a vector with coordinate 1, 1, 1 everywhere, is in the cone, in the relative interior of the cone, generated by the vector 1s. 1s are the vectors with 1 for coordinates belonging to S and 0 otherwise, okay? So it's just this. But in terms of game theory, you can say it differently. So you can rewrite this vector equation into n simple equations, and then you find that the sum of the weights for each player, the sum of the weights over coalition containing a given player is equal to 1 for each player, okay? So let's see now examples to clarify this. Of course, a partition in the usual sense is a balanced collection because you just put weights equal to 1 to each coalition, and then automatically you will satisfy this condition. Now, a more sophisticated example, let us take 3 players, consider 3 coalitions which are 1, 2, 1, 3, 2, 3. So it's easy to see that by giving a weight of 1/2 to each of these coalitions, you effectively see that each player has a total weight is equal to 1, okay? Because each player is appearing exactly twice in this collection, okay? So next example with 4 players, similar but with more complicated weights, but not all equal, okay? So this is a balanced collection. So you immediately see that it's very combinatorial because the partitions are already very combinatorial. This is much, much more. So in fact, it's too much combinatorial. So we must limit the things by considering only minimal balanced collection, which means the collection is minimal if removing one set, it's no more balanced, okay? Equivalently, they possess unique balancing weights. Otherwise, there are infinitely many. So, what about the knowledge about this minimal balanced collection? Their number is unknown. There is no formula. Contrarily to the number of partitions where there is a formula. It is a Stirling number. Here there is no, and nobody knows how many minimal balance collections there are. So recently there was, so for 4 it was known. For 5 you can find unpublished papers by Shapley, but that's all. Okay, so I will show you the number still 7 players because we have implemented the algorithm proposed by Peleg. And but you will see it's very time consuming and seems to be difficult to go beyond 7 players. So now this is a kind of digression. What about the opposite notion? Unbalanced, non-balanced collection. Is it interesting? So surprisingly, it is also interesting. This has been explored by Biera. And so the further definition is a collection is unbalanced if it does not contain a sub-collection which is balanced, which is not exactly the same as not balanced. There is a subtle difference. I will maybe not insist on this. And here the important notion is maximal collection, because you understand that the more you add, if you add more subset, finally the collection will become balanced. Because, why? Because 2 to n, the total collection of all sets is balanced, okay? So finally you will find a balanced collection if you continuously add new sets. So the interesting notion is the maximal unbalanced collection, okay? To which I cannot extend more. So this is a subtle difference, but I will not detail this. So this is what is known so far, till 9 players. You see that it is growing quite fast. And you will see later that balanced collections are growing even faster. So there is why is it interesting? So there is another way of defining them, a characterization, which is the following. So a collection is unbalanced if you are able to find a vector y, okay, so like a payment vector, in fact, okay, such that the total sum of the coordinates is 0, and the sum of the coordinates for all sets in the collection is strictly positive. So for example, this is unbalanced because you can find this vector, sum of coefficients is 0, and sum of the coefficients for all sets in the collection is positive. So, by this result, it is unbalanced, and you can check that indeed this is unbalanced. So this is a more complex example with 4 players. Okay. And now, what is the interest of this? It is related to what is called hyperplanes arrangement, which are used in some fields of physics, quantum physics, in fact. So it's better to explain this on an example. So let's see what happens with 3 players only. So imagine, you have the 3 axes x1, x2, x3. So this is a payment vector, okay? The space of all payment vectors. Now consider the hyperplane of all payment vector where the sum is equal to 0. So it's kind of oblique hyperplane, okay? And now in this hyperplane, imagine the planes defined by this equation. x1 plus x2, or x of s in general, is equal to 0. So this defines planes. In fact, here they are just straight lines, okay? And they define regions, because you can consider the region where x1 plus x2 is positive and the region where it is negative, okay? Due to the condition that the sum of all coordinates is 0, you automatically have x3 is equal to 0 also. So by the arrows here, I just indicate that if you go into this direction, then this sum is positive. If you go to the red arrow direction, then x3 is positive. So now you see that you have similarly 3 straight lines, okay? And these straight lines define 6 regions. Let us take, for example, this region. It is defined by x3 is positive, x2 is positive because x2 is equal to 0 is here. And also, we are in this half plane here, where x1 plus x3 is positive. x2 plus x3 is positive, okay? So this region is characterized by these 3 inequalities. But remembering this result, you see that it defines an unbalanced collection, which is exactly this one. 2, which is correspond to this arrow, 3, and 2, 3. So each region corresponds to an unbalanced collection. This is a connection between unbalanced collection and hyperplanes arrangement. Okay? So now back to the balanced collection. So with Dylan Laplace-Mermoud, with PhD student and my co-author Peter Sundolter, we implemented the Peleg algorithm, and we were able to find this table. And as you can see, it seems difficult to go beyond, at least with our small computer. Okay, maybe by using some parallel device, we can go till 8 players, okay, we hope. But for the moment, this is the result. So you see that the number is increasing very fast. So we checked that this sequence of integers was new and unknown, and effectively it was the case because it is not in the online encyclopedia of integer sequences. So we added to this encyclopedia, and now you can find this sequence under this number. And also we have the list of all minimal balance collection for till 7 players If somebody is interested, we can sell the file, but it's very big. Okay, so the question is, can we do better? Because maybe it's not the only way to get this minimal balance collection. Effectively, it's not the only way, because it's not difficult to see, not entering into the details, that if you consider this polytope, defined by these inequalities, in these inequalities you see it's just nothing else than the definition of balancing weights, in fact. Yeah? So the vertices of this polytope exactly correspond to the minimal balance collection. So we transform the problem of generating minimal balance collection into the problem of finding the vertices of a given polytope. And for this, there are algorithms, for example, the Avis-Fukuda method, which is even available under this package. So we tested it, and apparently, with the Peleg algorithm, we do better, as you can see from the computation time. And even I don't think that you can go beyond because of memory size. With vertex enumeration, you cannot go so far, in fact. Okay, so this is the present state of knowledge about this. Yeah. So now what about the applications? So the first application is non-emptiness of the core, because the balance collection were created for this, in fact. This is the origin. So the famous Bondareva-Shapley theorem says that a game has a non-empty core if only if this inequality is satisfied for every minimal balance collection. Okay, so take one, let us call it B, with balancing weight lambda. So the sum of the lambdas multiplied by V of S should be always smaller than V of N. This is the condition which is called the balancedness condition, and such games satisfying this are called balanced. Okay, so this is known from 50 years ago. So this is a nice result, theoretically speaking, but so far it was completely unapplicable in practice, because nobody was able to get this list of minimal balance collection. Okay, so you may say, but this is very combinatorial, given that for 7 players there are 100 million of minimal balance collections. This is of no use. So maybe there is a better way. So the better way is, of course, linear programming, because everybody knows by the proof of this theorem that it's equivalent to solve this simple LP with n variables, and the number of constraints is exponential, 2 to n constraints. This is less nice, but hopefully this is much better than doing this. But it's not true, because we tried, and using the Bondareva-Shapley theorem with minimal balance collection is much faster than solving the LP. And why is it so? Because the main reason is that minimal balance collection do not depend on the game. So you can store the list, and they just take them and to check the inequalities. They don't depend on the game. Okay, that's the main advantage. Okay, so let's see other applications. So what about, yes, exact games? This is also an important notion related to decision theories. Exact games were proposed by Schmeiler, so it's something which is directly related to decision theory. So we say that a coalition is exact if you can find a core element, x, such that there is equality f of x of s is equal to v of s, okay? And the game is exact if this is true for every coalition, okay? So the problem is how to check this in practice. So I give you a game with 6 players, let us say, and I tell you, please check me, find all the exact coalitions. Well, it's not so easy, in fact. And related problem is effectiveness. So you see that the equality is the same, just the quantifier differ. So here there exists some x in the core, and here it is for all x in the core. So effective correlation is effective means that the core lies in this hyperplane. Okay, that's the meaning. So how to check this? If you use balanced collection, it's very easy. You define this game related. If you see the definition, it's almost like the original game, but you change just one value here, okay? Then you can say that the correlation is exact if only if this modified game is balanced. So it's very easy to check. And for effectiveness, it's even simpler. You just take all balanced collections such that there is equality here, and having all of them, the union of this balanced collection is exactly equal to the set of all effective coalitions. So it's extremely easy. Okay? So now let's see a much less simple application, which is core stability. So what is stability? So I must explain what is a stable set. And for this, I need to introduce some additional notation, just a little bit, and or another definition. So first, a notation. So formally, we spoke about efficient payoff vectors, vectors such that x of n is equal to v of n. So there is no waste. We share all the cake. Let us denote by x of v the set of all such payoff vectors. Okay. Now a little bit more restrictive, an imputation. So it's the same, but you impose in addition that each payment given to a player is at least equal to v of I for this player. Okay. So now take 2 payoff vectors, efficient. We say that x dominates y via a coalition S if 2 conditions are satisfied. First, x is strictly better than y for all members of this coalition. Okay? And second, the coalition can afford this vector x in the sense that, remember that v of s is a benefit generated by the coalition S. So if x of s is smaller than v of s, the coalition S can afford this vector x. Okay? So you understand that if a payment y is proposed, and if x exists satisfying this, then S will object to payoff y, saying, but we have a better one, x, so we don't want y, we want x, okay? So the notion of domination is very important. And we say that a vector x dominates another vector y if you can find a coalition via which x dominates y, okay? So now the idea of genius of von Neumann and Morgenstern was the notion of stable set. So U, which is a subset of imputations, is a stable set if it satisfies 2 conditions. First one is external stability. It means that if you take a vector outside U, then it will be dominated by a vector in U. Okay? Second, if you take two vectors in U, they cannot dominate each other. Okay? This is a stable set. The notion was very clever, very interesting, but unfortunately, it reveals to be extremely difficult to use in practice and even in theory, because finding the stable set of a game is very difficult. And sometimes they do not exist, stable sets do not exist. But again, it's extremely difficult to find counterexample. The simplest known one has 11 players, so it's something terrible. And when they exist, they are not always unique, even not convex, not connected. So it's something very difficult to use. But there is an interesting fact, is when the core is itself a stable set, then everything is going well, because it is a unique stable set. And since the core is convex, it's a polytope, it's not so difficult to compute, then you have the perfect solution. Okay? But the problem is that nobody knows until recently how to check if a given game has a stable core. So recently with Peter Sudolter, we found a condition, which is if only if, and this condition is a finite one, but it's very combinatorial. Let's explain, and it involves minimal balance collection. Let's explain how it works, roughly. So if we look at the problem of core stability, what is the logical statement for this? You have to answer the following question. For every y, vector y outside the core, there exists a vector inside the core dominating y, which means there exists a coalition S where you have these strict inequalities and this equality x is equal to v of s. Okay? So if on the complexity point of view you have two quantifiers on uncountable sets plus a finite set of linear inequalities. Okay? Plus also another quantifier, but not a finite set. Okay? So it does not count it. So now compare this to the problem of checking if the core is non-empty. Then you must answer the following statement. There exists an X, efficient payoff, okay, such that all these inequalities are satisfied. This is a finite number. So there is here one quantifier on an uncountable set plus linear inequalities. How is it solved? By the Bondareva-Shapley theorem. It means you reduce this to a finite test via minimal balance collection. So the reflex is to say, okay, so let's try to do the same. Here we have two quantifiers, so let us apply a kind of balance condition for this one, for the inner condition, and for the outer condition here, we will have a second level of balancedness condition. That's why we have a nested balancedness condition. That's roughly the idea, but now the details are more complicated, essentially because for this outer level of balancedness, we need something a little bit, not only a little bit, something more general, in fact, which is called balanced set. So remember the definition of a balanced collection. It means that the vector 1n, the vector with 1 everywhere, is in the relative interior of the cone generated by vector of the form 1s. So if we replace one S by any vector with positive coordinates, then you have the definition of a balanced set. So it's much more general. Unfortunately, we need them for our condition, and unfortunately also, there is we didn't find any algorithm to generate them, because Peleg algorithm is not adaptable to this case, and the only thing you can do is to take all this linear system and check if there is a unique positive solution, which is very time-consuming. So here is the result. I don't comment on it because it's a bit complicated to introduce the notation. You see the double balancedness condition with, maybe I skip the explanation, it's too long. And so we have implemented it, and the results are not so satisfactory, because for some games we found in a few seconds the answer, the score is stable or not stable, and for other games it takes hours, days, and we are still waiting for the answer. So there is still some progress to be done on this theorem. Okay. So now I go to the last section, which is the geometry of the set of balanced games. So balanced game is a central notion. How looks the set of balanced games? This is a question apparently not explored so far. So this is a joint work with Pedro Miranda and Pedro Garcia-Segador, which is still so it's under work. So you may ask a question in different forms. So the first most natural one is to say, what is the set of balanced games? That's it. So let us call it BG. Okay. So, but then you can impose some additional constraints. For example, you may say that, but I want that V of n is equal to something. Okay. Okay, why not? And then you can say, but I want that my games are with positive coordinates. Okay? And then finally you say, but I am interested into capacities. So it's positive coordinates plus monotonicity conditions. Okay? So we were able to completely describe the geometric set of balanced sets in the three first case, but unable to do it for the last one. It seems to be very difficult to study. And here I will just focus on the BG plus with positive coordinates and BG set of balanced games simply. Okay, so notation I will use from now on is this Gothic letter B star. It means simply the set of all minimal balance collection, except the collection N itself, because we can discard it. So if we are interested into BG plus, this set is defined by a set of inequalities, which is the following one. So you take, the first line is simply the balancedness condition. So for each balance collection, minimal balance collection, you must satisfy this inequality, assuming that V of n is equal to 1. And then the game must take only positive values. Okay, so this is evidently a polyhedron because it's linear inequalities only. It's also evidently bounded because you have inequalities in the two directions. Okay. And so the question is, what are the vertices of this polytope? So we were able to find them. This was not so difficult. It's relatively easy to show that a vertex of this set must be, of course, a balanced game, but also a 0-1 valued game, taking only values 0 and 1. Second, so the second result just characterizes them. It says specifically that the game V takes value 1 on coalition S and so on, and let us call D the collection of these sets where the value is 1. Then the only condition is that the intersection of D must be non-empty. And this characterizes completely the vertices of this set. So it was not so difficult to elucidate. And this, as a byproduct, you get the dimension of the core. So if you take a vertex with collection D, characterizing it, you immediately know the dimension of the core because it's simply the cardinality of the intersection of D minus 1, which means that if the intersection is just a singleton, then the dimension of the core is 0, so it is a point. And this is very particular. Okay, and also we are able to find the number of such vertices. There is the formula, recursive, and here is a table giving the results. So you see that it's increasing very fast. Yeah, so for example, for 4 players, there are 471 vertices. And just to tell, we wanted to study the set of balanced capacities. And so we computed by vertex enumeration the number of vertices for 4 players, and we found it 5,000. And then we thought, so this is no way to solve this. Because the vertices are not 0, 1 valued, they are completely, looks arbitrary. So we abandoned this idea to study set of balanced capacities. So now let's turn to BG, the set of balanced games without any restrictions. So they are defined by the following system of inequalities. You drop the second line. And so this is a polyhedron, but now it's unbounded. And so it's a cone. But how is this cone? To describe then I need some small additional notation. So first something which is well known is the notion of unanimity game. So you take a coalition S and you define US, unanimity game centered on S is simply a game such that its value is 1 for every superset of S, okay? And the direct game is very similar. It's equal to 1 only for S, otherwise it's 0, okay? Both sets of games constitute a basis of the vector space of games, okay? So what we found is the following. BG is a polyhedral cone which is not pointed, which means it contains a line. Okay? So it's not like this. It contains some vector space. And this vector space, which is called the linearity space, has dimension n. And here is the basis. So it's simply all unanimity games centered on the singletons. Only this. So the structure is the following. It is the sum of the linearity space plus a cone which is pointed now, and we call it BG0. So this BG0 is not unique. You can choose infinitely many BG0. We choose one such that the components of the singletons are 0. This is much simpler. And so you get something like this, in fact, okay? So this is a linearity space, so it looks like an open book, okay? And the supplementary space, BG0, is a pointed cone with extremal rays. And the extremal rays are given here, so we were able to find them. So apart the rays in the linearity space, you have in fact, surprisingly, all the direct games for S not being a singleton, and also these rays, which are some of the direct games, okay, for a kind of filter, it looks like, okay. So this is complete characterization, and surprisingly, if you take any of these extremal rays, they have core reduced to a point. So the question, it was tempting to study under which condition you get a core with a single, which is reduced to a single point. So this is the last question I would like to address in this talk. Under which condition does the core reduce to a singleton? Okay. Because in BG of n, all extremal rays have effectively a point core. But in BG plus, it's not always true. If you take, because the dimension of the core is the size of the intersection minus 1. So it's not always a singleton, okay? So first result, which is obvious, if you go to the interior of BG plus or BG, of course, core has not dimension 0. So now, in the case of BG plus, we were able to find this result. So let's see the most general form immediately. So it's a polyhedron. So take a face of this polyhedron, polytope. And we found that all the games in the face have a point core, if only if the vertices, all the vertices defining this face have a point core. So this is the result. Now for BG, so there is no vertice, but there are extremal rays. What is the situation? So first, if you are in the linearity space, the red line, then every game has a point core. What about the facets? Okay. For the facets, the result is also easy. It's the following. So take a facet. The facet corresponds to a minimal balance collection. Okay, there's bijection between the two. If the size of the collection is exactly n, then all the facets, all the games in the facet have a point core. If it is not true, then all the games in the relative interior of the facet, so no such game has a point core. Okay? And a little bit more generally, if you take a face, which is an intersection of facets, you found that the game in the face has a point core, if only if the rank of this matrix is n, which is just a generalization of the above condition. So let's, now maybe I have no time. So this is just an example with 3 players, which gives the exact structure of where, for which facet and which face the games have a point core. It is the blue region here. Okay, so maybe I stop here. Okay, thank you.
Thank you very much.
Thank you. Just a quick question. Can you use these ideas to compute the Shapley values? And I'm asking that because, you know, in the field of explainable AI, they use Shapley values,
yes.
And then the players have the features, but then they need approximation to compute the Shapley values. So maybe this is more sound.
I know this problem, but I don't think you can use this result because yeah, the Shapley value is not always in the core. So only for this reason, it means that you cannot use these results.
Okay, thank you. Thank you.
Hi. Sorry, I don't have much choice. So this reminds me of work that we did around 2005, 2006, looking for extreme lower probabilities. And so I think it's exactly the same problem, but with different constraints. So when you were showing these numbers, I thought, hey, what were the numbers I got? So I looked at some numbers, and for example, we in some sense started where you stopped. So you said we couldn't look at capacities, that was too complex.
Yeah.
What we started with was the completely monotone capacities, which are in some sense trivial, because there's to the power n minus 1 there. But then you can go to monotone, and then it becomes interesting again. Or and then I had a number for two monotone for 4, which is only 50.
Okay, so
and then you can do k minus 1 monotone, k minus 2 monotone, and things like that.
Okay.
And we also looked at ones for avoiding shear loss and for coherence. And there we found different numbers. So once you go to avoiding shear loss and coherence, it becomes more complex again. And so the numbers, for example, for coherence for 4, the space of 4 was 402 extreme points. So again, you see the kind of complexity, and we had to use vertex enumeration to be able to do that.
Yeah.
And with 5, the computer
interesting.
But so there's a lot of similarities in the type of things that you've been doing then for games, which what you can also look at for lower probabilities, and this can be extended to lower previsions. And similarly for the geometry, so at that point we looked at the geometry of some of the more simple cases by exploring the adjacency graphs. So you've got these extreme points, and you can look at the adjacency graph.
Yeah, so the adjacency relation is in general difficult to study, but it gives a lot of information. And we have still to do this into this set of balance endgames. Because,
so for me, the adjacency graphs were very useful to better understand the geometry of these polytopes. So perhaps this is also useful for you. And I'm going to look at Bondareva-Shapley and the Pelican algorithm, because that might give me new ideas. So thank you.
Thank you very much.
Any other question? Remark? Much.
Well, first of all, I would like to thank for the presentation. I think it is quite interesting, and I think it is interesting from the people from IP to understand the language and the terminology from games and vice versa. So related to this, I would like to ask you about the following. Imagine that you have, because you said at the beginning that lower envelopes of course define lower probabilities, but you can say even something more informative, because lower envelopes of course determine lower previsions. And I wonder whether lower previsions are interesting in the game field, because, for example, imagine that you have a game with more than 3 players, one of them that is super strong. So player number 2 and 3 decide to go together, but they say that they want at least as much money as the first one. So this is a condition that cannot be modeled using a game, but you can model it using a lower prevision. So I wonder whether this can be interesting in the field of games.
Okay, so this is the case where you have a set of imprecise of probabilities where
so you
does not correspond to the core of something. Yeah,
you have a set of probability measures.
Yeah, it does not correspond to the core of something. Yeah, that's your point. Yeah,
yeah, you take lower envelopes, but not on events, but on random variables, on gambles. So you have kind of a lower bound of an expectation operator. Yeah. So there are some conditions that I find quite reasonable in a game that cannot be modeled using a game or a capacity, but it can be modeled using lower previsions. So I don't know if lower previsions can play an interesting role in games.
Yes, certainly it should be interesting to study this and to see if we can study similar notions for this kind of I think it would be interesting to do that. Yeah, sure.
Other question? Remark? I have just a quick question. Could you say something about the equilibrium on games? And in a special situation for specific games, because maybe also this can be relevant with the connection of IP. For example, when you have particular lower probabilities or lower expectation, where the core, where the lower expectation is to monotone, and so you have the core, there the connection, and the connection also with Choquet integral is more significant. And since you work a lot on it, I don't know if you could advise something about the connection of equilibrium in games and with the computation by means of Choquet integral.
By equilibrium, you mean because it's, for cooperative game, so there is no really notion of equilibrium. So what do you mean exactly? It's
sometimes in ambiguity, some equilibrium are defined again, but maybe, I don't know if the question is too far, and so we can speak also later, or no?
So if you want to see the connection with the Choquet integral, so apart the things which are already known on two monotone capacities, I am not sure that this notion I have presented here have an impact and can be applied to the finding lower expectations of Choquet integral and things like that. So this I don't see for the moment any relation. Yeah.
Okay, thank you. Any other question? Remark? So thank you again for your
Thank you for your attention. Thank you.